Okay, so this is the reading group for PDF-WuKong. It is a large multimodal model for extracting and parsing information and answering questions related to PDF files. So our first presenter is Nora Yang. So over to her.
I guess Nora had some technical difficulties. She's joining again. Yeah, Nora, over to you.
I-
Nora,
I'm joining. Uh, could you guys hear me?
yes, we can now.
Yeah, we can hear you.
Okay, great. So let me start again. Document understanding has been a crucial task, especially for processing complex PDFs with interleaved advanced language models have brought significant improvements for text-based text, still fit content.
All right. So
Yeah, I think we should uh, let's proceed with the flow. So there are exist the main challenges while using text-based models. We generally lose the text-based models cannot read images properly, so we generally lose accuracy points on that. And the visual models, well, they are heavily reliant on tokens, and they cost a lot of credits. And again, those are not really scalable. So these are the few challenges that we face in the existing methods. So like these are a few examples of the current work that has been taking place, like the long llama models, Unidoc model, and the HIVT5 models. So these are the current state of the arts. Now let's talk about the main idea for this PDF-WuKong model. Now it revolves around the idea of using interleaved. Could you move on to the next slide, please? Yeah, so let's talk about the current idea for this model PDF-WuKong. So it revolves around the idea of using interpreted document parsing, sparse sampling, and multimodal language models. Instead of the vanilla method of passing the entire document as text, this model leverages passing, let's say the first page as text, and then the second as image, and so on until the end of the document is reached. By default, the text blocks are categorized as paragraphs, and the figures and the tables are identified as images. These are then organized into an XML file in the order of the document given to us. Now, coming up to sparse sampling. Let us first understand what does sparse mean. Well, in the context of computer science, sparse data generally refers to the data when most of the elements are, are either zeros or null. That is, they are absent. Now, what does sparse have to do with this document in question here? Well, it refers to the fact that most of the query that the user does. Now, what do you mean by query? Let's say I'm a user and I want to, let's say, know something about this document. Now, I'll give in a query. I want to know this about the document. So this is my query, and when I'm doing this, obviously the answer that I am expecting won't be dependent on the entirety of the document, rather than a small portion of it. So there's a lot of noise in the data with respect to the user. Hence, it is called sparse sampling. So we have to filter out all the irrelevant details. Another reason to leverage sparse sampling is that while dealing with large documents, the computing resource can grow significantly and hence increase the computing costs. Now, the pipeline consists of parsing the documents into text and images, then encoding them to embeddings, then select the relevant content using similarity searches, and then finally query that to the MLLM to get the results that we want. So let's say we have a document. It is converted to n number of text chunks and m number of image chunks, which are then input to and the user input query Q. Now we first extract the positive and negative samples of the query using similarity matrices, using the pre-trained paper PDF model. Then we randomly select two text blocks and images blocks, and then embeddings are generated, which is then passed to the multimodal LLM model. Now, coming over to the algorithm of the PDF-WuKong pipeline. Uh, a, we input a PDF document and a query given by the user, and we expect the answer, reply to the query. Now, we first parse the document into interleaved images and texts and images. Then we cache all the vector embeddings and create the embeddings for the user query as well. Now we use similarity matrices between the query and the cached image and text embeddings using the pre-trained paper PDF dataset. And then we fetch the top key elements, uh, and then these top key elements are then passed over to an LLM model, which then generates the answer desired by us.
Okay. So the way this works is, we have a document, we parse it. By parsing, we extract the text and the images, and then we encode them, both the text and the images, and pass this shared feature space to the language model so that it can answer the query. To train this model, what we have to do is, we compare the query, the embedding for the query, and the dataset embedding, and we use contrastive tuning to be able to differentiate between the good answers and the bad answers. So after calculating the similarity for the query and the text, we do not only want the model to be able to answer, but also select which answer is the best one. So the objective for this training would be that we have a representation loss, and then we have a loss for the question answer. So the quality of the answer depends on this equation for the loss. This is the representation loss. So let's focus on this numerator. This EQ represents the embedding for the query, and this EI represents the query of the positive sample, which is the answer that we want. And then we calculate the similarity. This could be cosine similarity. We then normalize it with the temperatures, with some temperature scaling. And in the denominator, we have this exact term as well. And we have this summation where EJ represents the negative sample embedding. So it does this for all the negative samples. And then we take its logarithm, because we raise this to with then exponential. And then we sum it over all the positive samples, and then we divide it to get an average loss by the total number of positive samples. So for the other loss, that is the question answer loss, here the LLM is given the embedding for the positive sample. It is also given the text chunk, and it is given the user's query, with which it generates an answer. That answer is then compared with the ground truth, which is available in the dataset. And then we use cross entropy loss to measure the question answer loss. So this cross entropy loss is almost de facto for classification purposes. Our task is very similar to that, so it makes sense. And and as we saw that we needed some positive samples and negative samples. We also want a data set that is multimodal. So not many datasets exist for these purposes. So the authors introduced their own dataset, paper PDF. It has two categories. One is single evidence and the other is multi-evidence. And we can see from this that it is a huge dataset, not huge compared to the current standard, but it is still a large dataset. So with single evidence, what it means that the question can be answered based on a single text of chunk or an image chunk. So if the question can be, the answer to the question is available just by finding one paragraph or some other chunk, then that is single evidence. But sometimes the questions are complex. It requires referencing multiple portions in the, it requires multiple portions in the document. That is multi-evidence. And to construct this dataset, the author used an open source library for parsing the PDF, and then created two categories, a single evidence set and a multi-evidence set. So far, this only contains the text and the images. Then it passed that to Gemini model to automatically generate questions for relating to those paragraph and images and its corresponding answers. The authors also used GPT-4 for the test set so that the quality can be much better, but Gemini was used because of its cheap price and more large scale use for the training set. And finally, the authors compared the result of this PDF-WuKong model with both open source and closed source model on several benchmarks. And the number of parameters is 8.5 billion, which is on the higher end of the spectrum for what the comparison holds here. Again, this does not apply to the closed source model, which has several hundred billions of parameters. And it can be seen that for almost all benchmarks, the PDF-WuKong perform better. And the data sets that were used were doc-vqa, chart-qa, which requires answering questions based on charts, images, and the author also compared it on multi-page data sets. And finally, the authors concluding with the impact for the sparse sampler. It enhanced accuracy with efficient token selection. This is because instead it stored all the features in a sparse feature space, and then it has an end-to-end integration which showed further gains. And that's it. Thank you.